last day's lecture, we talked about Maclaurin series and Taylor series of functions. Gave you a function f of x, asked you to find its Maclaurin series or its Taylor series. The Taylor series and Maclaurin series were series that, if you took more and more terms in them, they approximated the function that you're finding the Maclaurin-Taylor series of more and more closely. Today, we want to take a different point of view. We're going to talk about power series in section 10.4. A power series in X is one of the following forms. Summation n equals 0 to infinity, a sub n x to the n. So I wrote it out, a0, first term, second term, third term, and on they go forever. So notice the difference. Again in 10.3, gave you a function, found a series. Now I'm giving you a series in powers of x, and there's two questions you're going to ask. Two questions. And one is what you do for all series, basically. For what values of x does the series converge? We ask this of every series. We're talking in section 10.9. 10.9 was different in that it was a series of numbers. So all you did was ask, does that series converge or does it not converge? Here, in this series, are x's. All the a's are given constants to you, but because it has x's in it, we will now ask the question, for what values of x does it converge? Every value of x you put in here will produce a series of constants. Some of those series of constants might converge. Some of those series of constants might not converge. Our problem is then, for what values of x does the series converge? These values are called the interval of convergence of the series. And it's going to turn out that the word interval in here, there will always be an interval. Okay? It won't say like, this series converges for x between 0 and 1, and it converges between 9 and 10. That will not happen, because that's not an interval. That's two intervals. So it's going to turn out that every power series is going to have an interval of convergence, starting from one point and going to another point. It might be all the way from minus infinity to infinity, but it might not. Second question, that was the first question. Second question, in I, what is the sum of the series? So first of all, you decide for what values there is a sum, and then the second question you ask is, what is the sum? And when we were talking at 10.9, you'll remember that in general, it is very difficult to find the sum of a series. I'm going to give you a very nice way to answer the first question. It will be quite easy for us to find out what the interval of convergence is. What will be far more difficult will be finding the sum of the series inside that interval of convergence. So again, notice the flip-flop from again 10.3. 10.3 gave you function f of x, expanded in a series that we proved added up to the function. Here, giving you a series, asking when does it add up and what does it add up to? It's turning it around completely backwards. In 10.5, we'll join them together and and show we're talking about the same thing. It was just different points of view in 10.3 and 10.4. Now you have seen power series in X already. Is it not true that when examples, the Maclaurin series for sine X, we got it down last day. Sine X was equal to X cubed over 3 factorial, X to the 5th over 5 factorial, and on and on and on it goes. That is a power series in X, because you see powers of X and the constants. A0, this one happens to be 0. A1 is 1. A2 is 0. A3 minus 1 over 3 factorial, and so on. The Maclaurin series for e to the x. We had that last day. It is 1 plus x, x squared over 2 factorial, x cubed over 3 factorial, and on and on and on they go. That's a power series in x. It's not like this one. In this one, all the even powers were 0 missing. Here, they're all there. In fact, is it not true? Every Maclaurin series, we haven't done too many others, every Maclaurin series is a power series in X. So it's not too unfamiliar to you. For this one, sine X, what was the interval of convergence? What was that? Well, we saw last day, it was minus infinity less than x less than infinity. Interval of convergence here was minus infinity less than x less than infinity. Right? So this power series converges for this, that's its interval of convergence, this is its sum. This power series, right, converges, there's its interval of convergence, and here's what its sum is. So we've got a couple examples already of power series in X that we know all about. Here's another one that we've seen before, actually in 10.9, but with a different notation. Suppose I write the following series. So, examination, n equals 0 to infinity, ax to the n. I write it out, ax squared, ax cubed, dot, dot, dot. That's a power series in X. Any number, but we want a to be equal to 0. What's that? That's a geometric series that we saw in 10.9. And we know everything about geometric series. We know that this guy converges as long as the common ratio, which here happens to be x, is between -1 and +1. That's the interval of convergence. And what we know the sum is a over 1 minus x. So there's another example of a power series in X that we have already seen. Right? Let me call this one 1, this one 2, for reference in a minute. Let's call this one 3. And 4, let's look at this one. N equals 0 to infinity, n factorial x to the n. First term is 0 factorial, and 0 factorial is always 1 to mathematicians. So the first term is 1, then it's 2 factorial, or then it's 1 factorial, sorry, which is 1, x, and then 2 factorial x squared, 3 factorial x cubed, plus dot, dot, dot. Now we have not seen this one before, but we saw something like it. Remember back in section 10.3, we talked about this sequence. We showed in 10.2 that the limit of this sequence is 0 for any x whatsoever. We actually used that last day twice when we were proving that this guy converges to that guy, and this guy converges to that guy. When we looked at the remainders, we used that fact both times. Now, if we look at this one, what what is that trying to tell us? The fact that this is going to 0 is telling you that no matter what x is, these grow faster than those. Well, what does that mean here? If these factorials grow faster than those, what does it mean about the terms here? It means the terms are not going to go to 0. Remember we had that nth term test. If the terms of a series do not approach 0, then the series cannot add. So we could say here, since the limit as n approaches infinity of n factorial x to the n is not 0, therefore series diverges for all x by the nth term test. So there then are 4 power series, one of which converges for all x, another one converges for all x. That's the interval convergence. That's the interval convergence. This one does not converge for all x's. It only converges for x between -1 and 1, and this is its sum. This one doesn't converge, right? Except there's a little bit of a problem here. I said that does not equal to 0. Series diverges for all x except x equal to 0. Except x equal to 0. When x is equal to 0, 0, 0, 0, it converges to 1. The first term is the only term that's there. Right? But that is the only exception. So this series converges only for x equal to 0. In fact, could we say that about every power series in x? It converges for at least x equal to 0. It may converge on a finite interval like this, and it may converge on an interval like these two here. In fact, these are the only 3 possibilities that there are. There are only 3 possibilities. Possibilities for interval of convergence. And these possibilities are: 1, series converges only for x equals 0. This is the worst possible scenario. In fact, then, if that's true, the series basically is useless. That was our n factorial x to the n. Second possibility, which is the best possibility, series converges for all x. So here you could say I consists only of x equal to 0. Here we would say that I is minus infinity less than x less than infinity. That's the best possible scenario. That was the sine one, and that was the e to the x one. Converge for all x's minus infinity to infinity. And the third possibility is like the geometric one that we had here a moment ago. There exists a number r greater than 0 such that, and in the geometric series, that r was equal to 1, such that series converges for all x in absolute value less than r. That's what we saw for the geometric. X is between -1 and +1, absolute x less than 1. Diverges for all x's in absolute value greater than r, and may or may not In that geometric case, it did not converge at plus or minus 1. There are examples where it might converge at x equal r and not minus r. It might converge at minus r, does not converge at r, converges at both of them, and converges at none of them, either one of them, right? There are examples of those. Here, we call r the radius of convergence of the series. Now you might think, we drew a little picture here. Here's the x-axis, here's 0, here's r, and here's minus r. You get convergence in here, guaranteed. You get divergence out here, guaranteed. You get divergence out here, guaranteed. And here, maybe convergence, maybe not. So we call this length here the radius of convergence of the series. That wording is chosen because we could do all of this with complex numbers, talk about complex power series. In which case, then, instead of having an interval of convergence, you would have a circle of convergence, and this r will be the radius of that circle. So that's where the terminology comes from, is in a complex setting. So here, you might say that r is half the length of the interval of convergence. We could say that, but we don't. We call it the radius of convergence. We want every series to have a radius of convergence. So we're going to assign this one here. We're going to give r a value. What do you think a reasonable value would be for the radius of convergence of that series? And I think you're all going to agree it's got to be 0. Here, we're going to say that r is equal to infinity. Now, I'm not trying to say here that that's proper English, proper mathematics to write that, right? But we know what it means. All you're saying is, by writing r equal to infinity, you're saying this is the interval of convergence. By writing r equal to 0, you're saying this is the interval of convergence, and the only other possibility is this third one. So every power series now has a radius of convergence. If r is 0, the series is useless to you. It only converges at r equal to x equal to 0. If r is equal to infinity, fantastic. The series converges for all x, like those two guys. And the third possibility, which is the most common, we haven't seen too many examples of it yet, is number 3 here, where it converges between minus r and r, diverges out there, and may or may not converge at plus or minus r. This is the most common scenario, is number 3, and we're going to see it time and time and time again. It's not optimum, this is optimum, right? Having a conversion from all x's, but not all power series do that. Would you agree that if you know what r is for a cup series, if you know its radius of convergence, you practically almost know what its interval of convergence is. If you know that r is equal to 0, you know that this is the interval of convergence. If you know that r is equal to infinity, you know that this is the interval of convergence. If you know that r is a finite number, then you know everything about convergence except possibly 2 points. So knowing r practically tells you what the interval of convergence is, except in this scenario here. You'd have to check. These two would be called the endpoints of the interval of convergence. And knowing r tells you everything about convergence except at the endpoints. Agree? Again, I tell you how to find r, and I'm telling you basically what the interval of convergence is, except possibly at those 2 endpoints, and I'm prepared to tell you that right now. Theorem. The radius of convergence summation n equals 0 to infinity, a sub n x to the n, is given by either of the following formulas. Limit n go to infinity, absolute value, a sub n plus 1. Or limit as n goes to infinity, 1 over nth root absolute value a sub n if either limit exists. If either one of those limits exists, then you got your R. Now, I seldom ever use this one here. There are some special cases where this one could be handy. This one, by far, is the one that you want to use. All right? Now, be very, very careful. I've seen so many people go wrong with this formula because they don't read what it's saying. Question: what is a sub n? What is it? Because if you're going to use this formula, you're going to have to substitute for that, you're going to have to substitute for that, then you're going to take a limit. Basically, you're making a sequence here. Right? Remember I said to you once upon a time, we're not going to spend too much time on sequences, but sequences are the basis for everything we're going to do. You want to talk about a series? What do you talk about? Sequence. Sequence of partial sums, maybe. Sequence of terms. Now we got another one. Now we're in power series, you're going to say, look at this sequence of absolute values of this. In that sequence, it's got a limit. That's the radius of convergence of your series. And then you can write down what the interval of convergence is. What is a sub n? Answer. A sub n is sitting right here. It's that which sits in front of x to the n. It's the coefficient of x to the n. Remember that. It does not include the axis. It is not the nth term, right? It is what sits in front of x to the n. What's that? What sits in front of x to the n plus 1. That's what those a sub n and a sub n plus 1s are. And don't go around saying a to the n, okay? That's not the same thing. A to the n means a raised to the power n. These are subscripts. That's a sub n. Right? That which sits in front of x to the n. Right? For instance, examples. Our sine x. No, let's leave that one for a minute. E to the x. What was the Maclaurin series? If we wrote it in sigma notation, n equals 0 to infinity, x to the n over n factorial. I had it written out here, 1 plus x squared over 2 factorial, x cubed over 3 factorial. There it is in sigma notation. If we use this formula, r is equal to the limit of the absolute value of a sub n, that which sits in front of x to the n. That's 1 over n factorial. What is a sub n plus 1? What sits in front of x to the n plus 1? That's n plus 1 factorial. How much is that? Well, if we invert, we'd have n plus 1 factorial over n factorial. Don't need the absolute values now because they're both positive. And then we can do the following. Is not n plus 1 factorial equal to n plus 1 times n factorial? Isn't that, oops, factorial sign. Isn't that true? That 8 factorial is 8 times 7 factorial. 100 factorial is 100 times 99 factorial. Well, if you think of that, right, could you not simply say that? You're going to cancel all that. What you'd be left with n plus 1, and that limit is infinity. So indeed, the radius of convergence of the e to the x series is infinity. We already knew that. This formula is confirming it for us. What about our geometric ones? Remember we had that geometric series on the board a few minutes ago. We put it up again. Summation n equals 0 to infinity, ax to the n was that geometric series. If we go for r, limit as n approaches infinity of absolute value of a sub n. A sub n is what sits in front of x to the n. That's a. What sits in front of x to the n plus 1? That's a. Limit is 1. Yes! What we had on the board a minute ago for a geometric series. Fourth example we have summation. N equals 0 to infinity, n factorial x to the n. R. Limit. N go to infinity. Absolute value. A sub n, n factorial. A sub n plus 1, n plus 1 factorial. Do that same cancellation, cancel all that with all that. What's the limit now? 0. That's what we saw before by reasoning. Now it's obvious with this formula. Getting the idea? Getting the idea of how we use this formula then to produce the radius of convergence. Here, there's nothing to worry about. If we had this example and we didn't know about geometric series, if we didn't know about it, then we would say, we would know that this series converges minus 1 to 1, but we wouldn't know whether it converges at minus 1 or at plus 1. We know that because we did 10.9. Right? Clear? If a series has not been checked for convergence at its endpoints, of the interval of convergence. Now, that is not the case for the sine or for the e to the x series. There are no endpoints. It goes minus infinity. That is not the case for this silly guy. Because it only converges at x equals 0. It would be the case for something that looks like this. If a series has not been checked for convergence at its endpoints of general convergence, we say that the resulting open interval, so we haven't checked. So what you're really talking about is this third scenario where you've got convergence minus r less than x less than r, and you haven't checked out plus or minus r. If you haven't checked out and you talk about this, that's an open interval, is called its open interval of convergence. Because I'm going to tell you that it is very difficult for the vast majority of examples to check out whether you've got convergence at the endpoints. That can be very, very difficult. So you take a series and you substitute x equal r, and you get a series of constants. And you ask, series, do you converge? And remember in 10.9, how many series did we know whether they converged or not if they didn't? The answer was 2, geometric and harmonic. No other series was able to handle very well, right? Especially for convergence. I had the nth term test for divergence. That sometimes could be useful here, but I don't have many tests for convergence. There are sections in the book that deal with that, but we're not going to do them. So quite often, and we're happy to just know the open interval of convergence without knowing the full interval of convergence. We say we don't care, right? And this is especially true in our last topic, our second topic, of course, when we solve differential equations. We will solve differential equations, whatever those things are, on open intervals. And one of the most important techniques for doing that is something you'll see in Math 3, and that's using infinite series, power series, Maclaurin series, Taylor series, to find a solution of a differential equation. So you find this infinite series solution, you say, I don't care about the endpoints because I had to solve the differential equation on an open interval in the first place. I don't care about the works on the endpoints. So realize that. And what's important is, I hate to mention this, when it comes to test questions or exam questions, make sure you look and see, is the guy asking for the open interval convergence or the interval of convergence? If he's asking for the open interval convergence, say, forget the endpoints. Get the R, and you're going to be done. But if he says, find the interval of convergence, and there are endpoints, you got to check them. And make sure you do. So what I would like to do for the rest of the time today is take some more examples of finding intervals and finding open intervals convergence of various power series in X. So I have a number of examples here that I would like to do. So first, series is summation. N equals 0 to infinity, n squared, x to the n, over 2 to the n. Right? And I want its interval of convergence. So this one I'm saying then to you, make sure that you tag endpoints if there are endpoints. If R turns out to be infinity, then there won't be any, so you don't have to bother. If R turns out to be 0, you won't have to bother either. But if R turns out to be a finite number, there will be an interval convergence, there will be endpoints, and you got to check them. So here we go. First thing we want is the radius, because it's going to tell us just about everything except the endpoints. So absolute values, let's put in here, let's change a little bit. No, let's not. A sub n, that which sits in front of x to the n squared, over 2 to the n. That which sits in front of x to the n plus 1 squared, over 2 to the n plus 1. So now what we're doing all these calculations of R values. It's going back to section 10.1 when you were finding limits of sequences. We're doing that again, so everything you learned in 10.1, now coming back. Limit as n goes to infinity. If we invert and multiply, don't need the absolute values, we have n squared over 2 to the n plus 1 over n plus 1 squared. Take that limit. Well, I think the first thing we should do is say, cancel all of those 2's with all of those 2's except one of them. And now the answer should be staring you in the face. If you've done your work in 10.1, you would know that the limit of this one over this one is 1. Right? You can divide top and bottom by n squared in order to get it, but you should be beyond that now and say, that limit is 1, so the answer is 2. So the radius of convergence of this series is 2. So we can say, open interval of convergence is minus 2 less than x less than 2. It says, guaranteed it converges in them. Guaranteed it diverges if x is bigger than 2. Guaranteed it diverges if x is less than minus 2. What we don't know is what happens at 2 and at minus 2. Let's check it out. Let's look. At x equal 2. Series becomes, let's look at it. I put in x equal to 2. Summation, n equals 0 to infinity, n squared over 2 to the n, 2 to the n. And we cancel the 2 to the n's. And we ask, series, what do you do? Do you converge or do you diverge? Well, think about running out the terms. 1 plus 4 plus 9 plus 16. That series diverges by the nth term test. The terms aren't going to 0. Therefore, diverge, which diverges by nth one endpoint done. Now let's look at the other one. At x equal minus 2, what does the series become? Summation n equals 0 to infinity, n squared minus 2 to the n over 2 to the n. Well, do you agree if I can break that up into minus 1 to the n and 2 to the n, and then I can cancel the 2 to the n's. So it's the same as this series, but every other term is positive and every other term is negative. Will they go to 0? No. So a series diverges again by nth term test. And therefore we can finally say the interval of convergence is minus 2 less than x less than 2. Neither endpoint is picked up. That is the full interval convergence. Up to here, it was the open one because we didn't check the ends. Now we check the ends, they're not in, and therefore this becomes the full interval of convergence. So again, the radius was the key. Finding it gives you the open interval, then you check the endpoints if they are desired. And here they were. Second example. Open interval. So this time we won't have it. There are endpoints. Open interval of convergence 4. Summation n equal, let's make it 3 to infinity, minus 1 to the n, n factorial, n to the n, x to the n. Getting somewhat more complicated than our previous examples of finding intervals of convergence or open intervals. Key again, find the radius. R, limit, n go to infinity, absolute value of a sub n. That which sits in front of x to the n. There it is. Minus 1 to the n, n factorial, n to the n. But replace all these n's by n plus 1. Minus 1, n plus 1. Plus 1 factorial over n plus 1 to the n plus 1. Limit. Let's simplify it. We can throw away all the minus signs because we've got absolute values. We've got n factorial over n to the n. We've got n plus 1 to the n plus 1 over n plus 1 factorial. Take that limit. Well, remember we did these factorials, we cancel. We can cancel all of that with that. But now notice you've got n plus 1s here, you've got n plus 1s here. I'll say I can cancel that one, knock that one off. So you're left then with the limit as n goes to infinity of n plus 1 to the n over n to the n. The question is, what's that? Here's it. Lock it down, here I come. Forget it, okay? Just don't even think about L'Hopital's rule of this. Besides, you shouldn't have to. Could I write this in the following fashion? Limit as n goes to infinity of n plus 1 over n to the n. Just the powers n, the powers n. And could I now write this as the limit as n goes to infinity of 1 plus 1 over n to the n? And now you better recognize it. That's E. We saw that way back in our first class. That's E. So we can say, therefore, open interval of convergence for the series minus e less than x less than e. It converges for any value of x between those. And we haven't checked the endpoints. The endpoints here would be exceedingly difficult to discuss. If I put x equal to e here and say, now let's examine very, very difficult series to determine whether it converges or not. But I didn't ask for it. Happy with that? One more example for today. Perhaps I should interject. Would it make any difference in this example if I put 33 here instead of 3? If I put 333? The answer is no. Okay? Where it starts is irrelevant for its convergence interval. Now remember also, there were two aspects to our series. One, find the open interval or interval convergence. Two, what's the sum? That, as I said before, turns out to be far, far more difficult, is to find the sum. For me to find the sum of this series for these values of x, not in a million years. Okay? There's no way I could do that. It is a much more difficult process to find actual sums. We'll deal with some of them later, but right now, that would be difficult. I want to look at the following example. Summation. N equals 1 to infinity of minus 1 to the n plus 1 over 4 to the n plus 2 x to the 3n plus 1. And I'm going to ask, I want the open interval convergence, and I actually want the sum. I claim that we can find the sum of this series. All right? But I'm not interested in the full interval. I want it as the open interval. Now, if I'm smart, I will attack the sum first, but I'm not that smart. I'm going to go for the open interval convergence. Then I'll come back and I'll look for the sum after that, right? So we know that the key is for finding an open interval convergence is find its radius. So I write over here my formula, r equals limit n go to infinity of absolute value a sub n over a sub n plus 1. Plug it in and evaluate. And the answer is, you can't! You can't. What was a sub n? A sub n was that which sat in front of x to the n. You got x to the 3n plus 1. You got a problem. You can't use that formula. At least not right away. But here's what we're going to do. We're going to take this series, and I'm going to pull out one of the x's, that one, and I'm going to write the rest of the stuff down. N equals 1 to infinity, minus 1 to the n plus 1, x to the 3n. And what I'm now going to do is I'm going to let y be equal to x cubed. Then the series, summation, n equal 1 to infinity, minus 1 to the n plus 1, x to the 3n is equal to summation, n equal 1 to infinity of minus 1 to the n plus 1, y to the n. I forgot something. I forgot all my 4 sub n plus 2's. And you notice I dropped the x, because that's not affecting where the series converges. It's just sitting up in front. So I'm looking at the series then without the x and saying, where this one converges, so does that one, and I'm changing this one into that one. And I said, oh, now we got y to the n. Let's go find the radius of convergence of this y series, and then after we get it, we'll look for the radius of convergence of the x series. So let's call this r sub y. Limit. N go to infinity. Absolute value. Minus 1 to the n plus 1. Over 4 to the n plus 2. There's a sub n. Now, increase the n's by 1. And what's that limit? Throw away the minus signs. Turn it upside down. 4 to the n plus 3 over 4 to the n plus 2. Cancel all of these 4's, cancel all of those, and the answer is 4. So the y series converges for these. This is the raised convergence. Now, well, we don't want that. We want the other. What I recommend is you do not turn this back into an open-ended convergence of y's. I'm going to write it here, but I don't want you to do it. See, minus 4 less than y less than 4. I've seen some pretty strange things happen when people do this, and then they start to put it back in terms of x. I see some really strange things. Don't do it. I would say, well, if y is equal to x cubed, then x is equal to the cube root of y, so my r sub x should be 4 to the 1/3. And now I can say, open interval of convergence is open interval of convergence is minus 4 to the 1/3 less than x less than 4 to the 1/3. That's the open interval of convergence. And that's all I asked you for. I didn't ask you for 4. I asked you for the open interval of convergence and the sum. So let's talk about the sum now. The sum of the series. We know it converges for those values of x. I said I could solve this problem. The best way would be to attack the sum first. We'll see why in a second. Do you recognize what that series is? Answer, it's a geometric series. You just have to kind of organize it a bit to see that. What does geometric series look like? They look like a summation, and there's some limit here, right? And then there could be something here, and then there's something here to the end. Looks like that. Where these somethings, no end, right? Anything here you want, anything here you want, integer here, right? So can you write that way? Well, let's try it. Summation, n equal 1 to infinity, minus 1 to the n plus 1, over 4 to the n plus 2, x to the 3n plus 1. I want to write it. Summation, n equal 1 to infinity. I want some stuff here, I want some stuff here, and an end there. No ends, no ends. Right? Well, how do I put a x cubed there? If I put an x cubed here, that would take care of x to the 3n, right? Then I'll put 1x in here. That takes care of that. The minus. How do I put up minus here? That would be minus 1 again, so I'll put up minus there. That takes care of those guys. What about these? How do I put a 4 here and a 16 here for the extra 2 4s? So do you agree, if I do all of this, I will get that? And I have now shown that it's geometric. Here's my common ratio, which says, hey, I can write down the sum. The sum is the first term over 1 minus the common ratio. First term. What is it? You put in here x equal 1. So you get minus x over 16 minus x cubed over 4. There's the first term. Common ratio, we said, was this, so we'll have minus an x cubed over a 4. There it is. There's the sum of that series. And in fact, because it was geometric, I can say that minus x cubed over 4 must be between minus 1 and plus 1. And that's not open interval, that's full. guaranteed was that this was the open interval conversion, and I didn't check the endpoints. Answer, if I do it this way, I don't have to check them. I know they're not in. So let's simplify this, all right, and see whether we get that. So first thing maybe do is multiply by -4. If you multiply by -4, you have to multiply by minus reverse. So this would be 4 greater than x cubed, greater than -4. I hate them that way. -4 less than x cubed, less than 4. And now if I take cube roots, -4 to the 1/3, less than x, less than 4 to the 1/3. That's exactly this thing here. And I got it with no r's. I did not have to go through all of this in order to get it. I simply had to recognize your geometric. And that was the fast way there then. Here's the whole solution. But I wasn't that smart to see geometric when I looked at it. All right. That's it for today.